Okay, thank you for asking me to talk over here. So I will talk about a novel tensionless limit for string theory on ADS3. This is based on a short note that we had earlier in the year with Matthias Gabriel and Chris Hull. So tensionless limits of string theory can help us uncover the unbroken symmetry phase of string theory, and that's one reason to try to study them. And of course, the hope is that by looking at this unbroken symmetries of string theory in an unbroken phase, you can try to say something, constrain the dynamics of the theory, even in the broken or Higgsed phase. So that's the broad motivation for studying tensionless limits. So there's something special about string theory on ADS3. ADS3 are special. Firstly, they are special. The first reason is not generic to ADS3, but to all ADS theories. ADS string theories, which is that there is a dimensionless coupling because you have ADS has a length scale, or cosmological constant, then you can take its string scale or alpha prime and this dimensionless parameter is something you can take to 0 and talk effectively a tensionless limit, because that's the limit where the string length is much greater than the ADS length scale. So this is the opposite of the supergravity limit that one normally considers, where this ratio goes to infinity. So this is something you can take in all ADS spacetimes, and this corresponds usually to a free theory in the dual CFT. Because this translates to something like Toffling. And so this limit is really a coupling going to 0 limit, and this is where people have explored this in various cases. Some of these John Simon's theories that you just heard about arose from considering duals of such higher spin theories. So typically what happens is that there is in this limit you get a set of massless fields which have higher spin, and that sector is described by these sort of Vasiliev-like theories. So there is a general uniform story for any ADS deep for which we know string duals. But there's something special about ADS3 in particular, which is that in the unbroken symmetry is much larger compared that for ADS D plus 1 with D greater than 2. So this follows fairly simply, and I'll just give you the argument because it's just a two-line argument. It follows from the fact that in the dual CFT, there's a unitarity bound, which is which goes roughly like for a spin S field in a CFT, the conformal dimension is bounded. So for CFT in D dimensions, you have this kind of a bound, which is saturated by conserved currents. So delta is equal to d minus 2 plus s, the equality holds for conserved currents. And conserved currents are the ones which are dual to massless IR spin gauge fields. So the states in the CFT which saturate this bound would correspond to massless spin gauge fields. And for d greater than 2, this is non-zero. The bound is satisfied only for bilinears in the free fields. Bilinears in the fields, I should just say. Because then delta minus s is something non-zero, and it's d minus 2, so in d equal to 4, it would be, let's say, 2. So the only twist 2 operators in the theory you can easily enumerate are just bilinears in the fields. So bilinears in fermions, or bilinears in the gauge fields, or in the scalars. So there's only a small set of such operators, but in d equal to 3, but in d equal to 2, or ADS 3, this is 0. So there can be many more conserved currents. In fact, because the bound is just delta equals to s, and these are just any holomorphic or anti-holomorphic currents. And there can be very large numbers of these, and for instance, in the case, so example, in ADS 3 times S3 times T4, which is a string background, supersymmetric string background, you have T4 to the n mod Sn as the dual CFT, and many conserved currents in this, and this was something explicitly we worked out, that a very large degeneracy of conserved currents which grow exponentially. So with the spin S, these are the conserved currents which you can show are single particle generators of this, and it grows exponentially. So it's a very large set of this. This is to the degeneracy in a Vassiliev 1. It doesn't grow with the spin in dimension d greater than 2. So the Vassiliev theories are a very small sector of this. So ADS3 is special because of this. And so there is a tensionless limit. This is a tensionless limit of string theory on ADS3, which has a very large degeneracy and which we have explored to some extent. But the question is, ADS string theories on ADS3 have a very rich moduli space. So are there other tensionless limits which are in some ways similar or different to the ones that you get from this kind of symmetric product CFT? So that's what I want to address. And the punchline, yes, there is a different kind of tensionless limit which is in fact also some under control, which shows very qualitatively, in many ways, different behavior from this. It will also have a very large degeneracy and so on, but it will look different, as I will try to explain to you. So for that, I have to tell you that I will focus on this kind of string background, though as we'll see, so you can have this as a concrete case in mind, though as we'll see, we'll actually not really need all this part. We'll be only focusing the string theory on ADS3 part. But theories like these have a very big, rich moduli space of parameters. This one is a 20 parameter space, and there are many limits. So there are many limits which are under control, which people study, where one has some control, analytic control over the string theory. So I'll just list a few of these just to give you the corners that people have studied. So first is, of course, the supergravity limit. Is the opposite limit as we discussed. This going to infinity. So this is a large radius limit, but this is something in which you have, so to say, Ramond-Ramond flux or NS-NS flux. There are, in these superstring theories, you can have these two kinds of three-form flux. So you can consider the supergravity limits in any of these cases. Then there is, of course, the symmetric product point. That's also an explicit, that's the one I wrote down, which is like T4 to the n mod Sn, and you can, so this is supposed to be a small radius limit because it's essentially like a free theory, and it has all these features. So this is one limit, but I won't talk about this in this talk. Then there is, well, there's another one which I'm just listing just because there's a PP wave limit under which you have control, again with RR and NS-NS flux. And finally, the one that I will be talking about is perturbative string with pure or three-form flux. So you can have an ADS3 with a uniform three-form flux, and this theory actually can be studied perturbatively, as I will just review in a moment. And so the question we will ask is, so this is the situation in ADS3 is special because those who have worked in ADS safety in higher dimensions know that usually you have only the analog of these points. You have a supergravity limit or some free Yang-Mills limit, maybe some PP wave limit, but you don't usually have an analog of perturbative string theory, even with if it is purely in a case with a special case with pure NS-NS flux, but still it's useful that there is a world sheet description of a full-fledged string theory, and one should be able to ask questions of whether this, since this is for any radius, in a sense. So this is a fully string, full string background for any R radius. So in principle, you should be able to ask this question, can we take a small radius limit and see what kind of tensionless limit there is, and is it similar or different? So what will help us is that this theory has been well studied, and in particular, The papers by Madhava and Upuri in the early 2000s gave a very exhaustive analysis of these string theories. So I will review this. It's a bit technical, the results, but it's very useful because other than flat space string theory, this is one of the very few string backgrounds that we have very explicit control over. So it's, especially for the younger people, it's a very good idea for you to familiarize yourself with this case, since it's a non-trivial string background, which has been quantized very successfully. So the reason this is solvable, because the world sheet theory is an SL2R level K Weizmann-Witten theory, a conventional Weizmann-Witten CFT on the world sheet, and SL2R because ADS3 is essentially the group manifold SL2R, so the target space is group manifold, and that's very special again to ADS3. And this K, which is the level, is related to this RADS square. I'll just put tilde because it's not precisely that, but at least for large K, it is proportional to RADS square by alpha prime. So this is so you can solve this theory for any level K. That's why I said RADS. This theory is known. You can compute the spectrum. You can compute the correlators. So there's a sort of series of 3 papers in which all this is done, Maldacena and Oguri. So this theory has a central charge C equal to 3K over K minus 2. Those who are familiar with the SU2 level K Weizmann-Witten models know that it is 3K over K plus 2. SL2R is sort of a K to minus K kind of rotation that very loosely speaking. So you can understand why this is the central charge. So the theory is basically, unlike flat space where you build up the theory from flat space oscillators, I hope many of you have studied string theory as students, but it's not clear that you have seen flat space oscillators. But alpha mu, you have these bosonic string theory. The simplest one, you have a simple 10 bosonic oscillators. Here in ADS3, the building blocks are oscillators built out of SL2R kinds. So target space is the SL2R. So instead of sort of flat space oscillators, you have oscillators JA. So A equal to, you denote it normally by minus and 0, or 3, notation I'm using. So, and these obey the usual current algebra. I'll just write down maybe some and there's the, well, I should have probably written the central term, which is the most non-trivial one. There's a current algebra which has this sort of central extension. The level K appears in this algebra, and the Virasoro generators are defined by the Sugawara construction. So the stress tensor is essentially proportional to is quadratic in the currents. So So you define, so this is the analog of the flat space oscillators, but now only in the 3 ADS. So typically you will have to have this plus some internal CFT, which we won't worry about. It might be these S3 or T4, whatever, the thing that completes it to form a critical string theory. And so that will have its own oscillators and so on, but we won't be so much interested in that. So the spectrum of the theory, when you quantize the world sheet theory, there are basically the states, the highest weight states. So the analog of, in flat space, you start with some momentum state and then you act by the oscillators. The analog over here is to act, are some SL2R representations. And these are labeled by 2 quantum numbers, just like SU2 representations are labeled by J square and 3. So this is quadratic Casimir labeled for SU2 like this. So there's the quadratic Casimir is built like usual from these J's, and you have so there's a quadratic Casimir, and this is the J3 J30 eigenvalue. So these are the states, and then you sort of act on it by so you have affine representations. So you generate so the oscillators J minus with negative modes, just plus minus 3, act on these ground states. So you generate a whole stringy tower of these states. So the good point. I'm just coming to that. So I didn't actually specify what SL2R representations there are. There are actually 2 sets of SL2R representations we need to consider. One which are called the discrete representations. And so this is unlike SU2, which is only discrete representations, SL2R has discrete and continuous representations. So these are a set of discrete representations, which we'll call dj plus. And so here J is, we'll take to be, so at the moment, okay, since I'm probably, we'll take J it was argued by Maldacena and Oguri that the J representations, that the J which labels these representations is a real parameter which goes from half to k minus 1 by 2. That's the J that appears over here. So then you have a state Jj, and you act by the 0 modes, you get J and then J minus integer. J plus minus integer. So you get the SL2R representation from this. So they're basically the M's are J plus or minus an integer. So that's one discrete set of representations that you need for the spectrum. But Sena and Oguri, what was realized was that you also have to consider continuous representations slightly differently. These are continuous representations of SL2R, and these continuous representations have basically J equal to half plus I times P. So that's why I'm using this label P over here, that the C hat, this thing is just 1/4 plus P square. So, and P is a real, this is real. So these are continuous series of SL2R, and here the M is, so alpha is now an independent parameter which labels again the J, this is the J30. So that's what I was calling M, but now this alpha is independent of J, so it's not related to J by an integer. Anyway, so 5 minutes. Okay, yeah. So what Maldacena and Oguri also realized was that this is not the full story. To get the full string spectrum, you actually need to consider what are called the spectrally flowed representations also. And so you have some A prime, a discrete representation, which are labeled by an integer W, which, so you have two infinite families of representations corresponding to each of these, which are labeled by an additional integer. And what are these? These are basically representations that you construct from a sort of so-called spectrally flowed generator. You define new generators which are equal to, J for plus minus is the original one, but the mode number is shifted by W. And for the J3, the mode number, you define new generators, which are shifted by some with a shift. So you define new representations with respect to these J2 generators, where think of these as your building block for these affine representations. So they are related to the original J's by this integer W, and you can build representations from them. So I think I was hoping to actually, because it was very simple, I was hoping to show how things really work with this spectrum. Okay, maybe let me. So then the physical spectrum is given by. So these are the representations. Then I have to tell you what is the spectrum, the space-time spectrum of states. That's given by the Virasoro conditions. L0 minus on physical state equals to 0, and Ln on physical state is equal to 0 for n greater than 0. And then there's a level matching condition. So you have to impose these to get the physical states. So the physical states, the J's, just like in flat space, these are the conditions that UP square is equal to some integer, and so on. The similar condition over here tell you that you have minus j into j minus 1 over k minus 2, which is, so actually here there's this Sugawara construction, you can see there's a 1 over k minus 2. So L0 gets a factor which is the Casimir, this Casimir divided by k minus 2, and then in principle there would be things from the internal CFT plus then the oscillators. So this is coming from the ground state, and then when there are there will be some oscillators, and there are SL2 oscillators and internal oscillators, and the whole thing should be equal to 1. We'll, for the moment, set these to 0, because we are anyway for so the goal is to look for states. Is there any point in the moduli space of this theory, as you vary k, where you get massless higher spin states? Okay, so maybe I don't have time to work it out, so I'll just state the answer. It's fairly simple. So are there massless higher spin states for some k? So presumably small k, because k was roughly like RADS squared by alpha prime. So if you just work out the condition for massless, so these give you the, then you have to write down what's the space energy and the spin in terms of this. Those are given by 0 or J3 bar m equal to 0, the left mover or right movers. So these correspond to energy plus spin by 2, energy minus spin by 2 in the space-time. So one of these being equal to 0 is this sort of condition, this delta equal to S condition here. So you just have to look for massless states. What you find is the only place, it's actually a very pretty answer, everything fits very nicely. The only place where one has massless states is at k equal to 3, which is at first sight a little odd, because you might have thought that k equal to 2 is sort of the place which is the critical place, the smallest radius. But actually it happens at k equal to 3. And what happens is, in fact, the graviton does not exist exist as a physical state. And this also doesn't seem to have been noted before for k less than 3. So for k less than 3. So k equal to 3 is, in a sense, a borderline, and you have extra mass state. In fact, there's at k equal to 3, an infinite tower of massless states. What is different from the tensionless case is that these are part of a continuum. I didn't actually have a chance to explain to you the physics of these continuous representations that appear here. These are called long strings, very long floppy strings which are on the boundary of ADS, close to the boundary of ADS. So in a sense it is, but typically there's a mass gap to exciting these for any finite k. So but at k equal to 3, this goes the continuum which goes down to 0 energy. So what the picture that you have is that at k equal to 3, you have a continuum which goes to 0. This 0 energy, and this happens only at k equal to 3. And then there are all these higher spin states, and these are massless in this sense that the energy is equal to the spin. This axis is the energy. And you have these higher spin states, an infinite tower of them for E equal to S, and there are massive states as well. So it's very much like you have in the over here, and in fact the degeneracy is also somewhat similar. It's part of a continuum, and this is very much like what one sees for there's a class of holography with normal model CFTs in which you have a tower of light which come down all the way to 0, and this is very much reminiscent of that. So it's a novel tensionless limit in which you have this whole continuum coming down because of these light states. And so it seems almost as if the string theory is in some ways singular at this point. But I think that's an interesting point whose physics deserves to be better understood. But you can see correlators which show some kind of singularity or pathology in this limit, because or whether when you go away from the pure NSNS flux point, you sort of lift this continuum or break this continuum. So maybe I'll just stop here since I've anyway gone over time.
So we have time for perhaps Subrat?
Yeah. So in fact, right. It's coming from that, but this is actually the particular one with W equal to 1, which comes down purely from the winding number 1. The other spectrally flowed representations also have continua, but they don't come down to 0.
So one might worry what happens if you move slightly away in moduli space.
This thing. Then I feel that this may be lifted, because the long string continua usually gets lifted away from this point in the moduli space, in which case it may look more closer to what you see from the symmetric orbifold point. So in the symmetric orbifold, you get this massless higher power, but you don't have this continuum. So this seems to be a tensionless limit, in which there is continuum and massless higher. So it's very much like, as you remember, the light states in the WN CFTs. If you take the usual sort of modular invariant, you have this whole continuum coming down to 0, but you have the higher spin states embedded in this continuum. It was just a Vasiliev sort of states. But here it's a whole stringy tower of such states, of massless higher spin states together with a continuum. So it's in some ways reminiscent of that kind of tensionless limit. So ADS3, I think, has these different tensionless limits. Maybe this is a singular one associated with the NSNS point of view, but that's probably a reflection of the WN CFTs, the same kind of similarities that are there, which also you can lift by going to a different modular invariant, is what happens when you go to the symmetric product CFT. So yeah, I think there is a parallel there between these different kinds of tensionless. Yeah. So this is preserved. I just worked it out for simplicity in that case, but there's a similar value of k there. It is, I think, equal to 1, which is in the supersymmetric case, the appropriate level. That's the one where you see the same phenomenon. Yeah. In the bosonic case, yeah.
So now, just to understand how you have.
Yeah, so the higher k, the continuum lifts. There's a gap. So the gap is proportional to k minus.
Remains a on some.
Yeah, so there's a delta, which is something like k minus. So at k equal to 3, the gap goes to 0, but at any other k, there is a gap. And that's the usual long string gap, what Seiberg and Witten also had studied as a sort of these extended strings. So this is there. The question about k equal to 3 is that this continuum comes down to 0. And you get massless states precisely at this point, and the graviton stops existing beyond this point. It's no longer, doesn't obey these sort of, this condition. It falls outside this range. You can see that k equal to 3, this becomes 1, and then you can't have the graviton anymore. And so this is really the smallest radius ADS you can have. And it has this sort of certain pathology, but it's not, I think, known or unseen pathology, and probably worth understanding better.
I think we've run out of time now. So